Hello and welcome all my advanced math friends. We're going to do some more stuff with statistics today. And really what I want to get into today are things called normal distributions. And so a normal distribution is when we have a histogram, and remember a histogram it's looks a little like a bar graph, but it's actually a frequency distribution. It shows how many are in a certain interval. And so there's many objects that when we study them, if we make a histogram of it, it always seems to come out to this same shape, where we have a lot of people right in the middle, and then as we get farther and farther away from that group in the middle, we have less and less and less people, which means what we get out of this is kind of this bell-shaped curve, which is also known as the normal distribution or Gaussian distribution. And so if we have a normal distribution, this is the way it'll work. We have our mean right in the middle, but since this is the most common entry as well, it's our mean, but it's also our mode because it's the most common. And since half the data, as you notice, is completely symmetric, so half the data is below this, half the data is above this, which means this is the piece of data that falls exactly in the middle, which means this is also the median. And so in a perfectly normally distributed set of data, the mean, median, and mode would all be the same number. Now, in real life, they might be off by just a little bit, but they're going to be really close to the same number if you have a normally distributed set of data. So what kind of data fits a normal distribution? Well, part of this comes into play. You have to have a large sample size. If you ask 5 people for information on something, it's probably not going to fit a normal distribution. But if you ask, say, 5,000 people, it's probably going to start to take this shape if you ask things like shoe size or height, um, amount of money they make. These are all things that would fit a normal distribution pretty well. And so this shape just seems to take form automatically. Now, since this shape takes form, we actually have come up with mathematics to analyze this and figure out what percent of data falls within certain ranges or certain intervals around the mean. Now, what this is based on is two things. Based on where the mean is, what value is the mean, and how spread out the data is. Because this curve would still work, but if the data is really spread out, instead of the curve looking like this, it would just be a curve that goes out farther but still has those tails at the end. And so this general shape works no matter what. The only thing that changes is how spread out it is, how far apart the numbers are. Now, how spread out the data is, we have a measure for that. We call that standard deviation. That's a measure of dispersion, of how spread out the data is. And so what we're going to use is the mean and standard deviations. Remember lowercase sigma, our cursive O looking thing, that's our symbol for standard deviation. And so it doesn't really matter what set of data we look at. If we go from the mean, that can change, remember, up one standard deviation and down one standard deviation. So in other words, we go within one standard deviation from the mean, both directions. That should encompass right about 68.3% of the data. Right? And then if I go 2 standard deviations away from the mean, that should encompass about 95.5% of the data. So we're starting to get to where most of the data falls within 2 standard deviations of the mean. If you go 3 standard deviations away from the mean, this is going to include 99.7% of the data. And if you go 4 standard deviations from the mean, it's like 99.99% of the data. So it's very rare to have an entry that's more than 4 standard deviations above or below the mean. Now, if this is the case on a normally distributed set of data, we could actually use this with a specific set and figure out what percentage should fall in a certain range. And this is done quite often on normalized tests like the ACT or the SAT, CLEP test, AP test, things like that, to get a normal distribution and figure out what is the average score, what's the standard deviation. And then you can even do percentile rankings. We'll talk about how to do that in a day or two. So let's see if we can do some of this with a specific example here. So give me just a second. Wait a second here. I just gotta do some looking here. Yeah. Don't you hate it when you're like at the grocery store and you're at the checkout and the person behind the checkout is just staring at their phone and you're just sitting there waiting Or say like you're watching a video of your math teacher and they're supposed to be doing some math problems, show you how to do math, and instead they're just staring at their phone and you're just like waiting. So today, what our example is going to be about is about screen time. How much time you spend staring at your phone. So a survey of 2,000 students asking them their daily amount of phone screen time is normally distributed with a mean of 5 hours and a standard deviation of 0.6 hours. And so the first step on one of these, this isn't a necessary step, you could possibly do this without it. I like to have a visual. And so the very first thing I did is I drew a picture of this distribution. Right, now since the mean is 5, I put that right in the middle. And then since the standard deviation is 0.6, here's what I did to get these other numbers. So this is basically the same picture as what we have going on here. The only difference is instead of saying mean plus 1 standard deviation, I know the mean and standard deviation, so I put in the actual numbers. And so the mean plus 1 standard deviation would fall at 5.6, because we have 5, the mean, standard deviation of 0.6. Go up another 0.6, that's the mean plus 2 standard deviations. Another 0.6, that's the mean plus 3 standard deviations, and I did the same thing subtracting the standard deviation from the mean. So with that information, and knowing these percentages we have over here, we should be able to figure out the answer to these. Now, some of these are going to be a little more straightforward than others. Something else that we need to keep in mind about the normal distribution is it is perfectly symmetric. So whatever happens over here, happens over here. Now there are like skewed distributions, they call them. We're looking at normal distributions that are not skewed in any way, so perfectly symmetric distributions. So what percent is between 3.8 and 6.2? Now here's what we have to think about. How many standard deviations did we go away from the mean? So did you notice we went 1, 2 standard deviations this way, 1, 2 standard deviations this way? Now looking back over here, if we go 2 standard deviations both directions from the mean, that includes 95.5% of the data. So in other words, that's our answer here. 95.5% of the data would fall in between those two numbers. So in this survey, around 95.5% of the 2,000 people we surveyed should spend between 3.8 and 6.2 hours on their phone. Now, what percent is between 4.4 and 5.6? All right, so now we're there and there. This is 1 standard deviation, both directions from the mean. So from what we found over here, if you go 1 standard deviations both directions from the mean, that's 68.3% of the data. Now something I'd like to do with this one is I'd like to ask how many people would that be in this survey then? And so if I say how many people are between 4.4 and 5.6 in this survey, well, we surveyed 2,000 people. And so basically we just want to take this 2,000 and take that percentage of it, which really simple way to do this would just be 2,000 times 0.683. Just make this percentage into a decimal, multiply it by 2,000. So in other words, this one would be around 1,366 people. Would be how many people out of the 2,000 we could expect to fall between 4.4 and 5.6. Part C, this one's almost a trick question. What percent is above 5? This is where remembering that this is perfectly symmetric comes into play. So if that's right in the middle and this is perfectly symmetric, doesn't that make 50% here, 50% there? And so what percent is above 5? Well, half of them, or 50%. And then this one, we're going the other way around on this one. What interval around the mean? So I'm asking for these numbers, basically, and telling you the percentage. So what interval around the mean includes 99.7% of the data? Well, looking over here, if we want to include 99.7% of the data and we want to go symmetric around the mean, that means we need to go 3 standard deviations above and 3 standard deviations below the mean. And so the interval that would be is going 3 standard deviations below, so 3.2 for the low range, up to 1, 2, 3 standard deviations above, and so that's 6.8 for the high range. And so the interval that would include 99.7% of the data is the interval from 3.2 to 6.8 hours. And then, just wanted to make us think a little bit. What percent is between 5 and 6.2? Now, do you notice we can't just use one of these numbers? Because all of these numbers are if we go both directions from the mean, the same amount. We're only going one direction from the mean. Do you notice we're going from 5 up to 6.2? However, if I go this whole length, 2 standard deviations, that's 95.5%, right? So if that's the case, this is where remembering that this is symmetric is extremely important. This is symmetric around the mean, so doesn't half of that 95.5% have to be on this side of 5, and half of that 95.5% have to be on this side? And so basically, if this whole thing's 95.5%, I just need to take half of that 95.5% to get this percentage. And half of 95.5% is 47.75%. So that's the percentage that falls between 5 and 6.2. Now, to give you an idea of where we're heading with this, I tried to keep this pretty basic since it's our first day talking about normal distributions, but what we're going to start to use are things called z-tables, and z-tables will let us have a percentage for any certain z-score, it's called, which is a certain number of standard deviations above or below the mean, and it'll just tell you what percent of data is from there down. So that's where we're heading with this later, but this is to get you a basis of how the normal distribution works.